Hey, how's it going there? Welcome to lesson 3.4. 3.4 says this. I can express the heat of fusion and the heat of vaporization as a for every statement. If we look at our list, 3.4 is here in the middle, and that's the one we're going over today. All right, let's go back to the notepad and let's get started. All right, so when I think of this skill, there's a scenario I kind of think about in my head, right? So here in the middle, we got the sun, and I want you to use your imagination here. So imagine you live on a farm, and metal workers on a farm use something called an anvil. This is made out of iron to heat metal, and then they kind of hammer it onto there into different shapes. And also on a farm, you'd probably find a jug of water because of all the work you're doing, okay? So let's say that one day Mr. Sun is out and you leave these two items side by side in direct sunlight, right? So this sunlight is radiating down. These rays are hitting both of these items. And we know from experience that when we personally are in the sun, we know that it kind of heats us up. So what I want you to think about is which item would heat up faster? So would it be the water? Would it be the anvil? Or would they both have the same temperature? Think about that for a second. Go ahead and pause the video, and then when you unpause it, we'll talk about it. Okay, so over time, both objects would reach the same temperature, but the object that would heat up faster is, drumroll, the anvil. And the reason for that is because we can obviously tell that water and iron are not the same things, and believe it or not, they have something called different heat capacities. And what this is really a fancy way of saying is this. They both have different rates of thermal transfer. Different rates for thermal energy transfer. So thermal energy transfer is unique to the item that you're specifically talking about, and it really just comes down to what material is it made out of. What you can even do is Google heat capacities on Google, and what it'll come up with is a list of quantified rates of thermal transfer. So let's go check steel here. Steel is 0.466, water 2.08. So I'm sorry, liquid water 4.1813. So basically, the higher the number, the slower the transfer of heat. So what this is telling us is that water gets hotter a lot slower than metal, and I think we've all seen this from experience. If you have a tea kettle, you put it onto a flame, we know that the outside of the tea kettle will get warm, but the water kind of lags behind. It takes some time for both of those temperatures to equalize, and then you get your boiling water to make your tea or coffee or whatever you need out of it. Let's go ahead and take this idea and take it one step further and specifically talk about water. So this is a list of energy constants specifically for water and water only. So H2O only. So water has three types of phases. We know that it can be a solid, liquid, or gas, and it also takes part in different kind of verbs, we could say. So you can melt or freeze water, or water can boil, evaporate, or condense. And what I want you to notice is that for every one of these actions or these states, water has a specific number associated to it. And what these numbers are, it quantifies the thermal transfer of water, right? So it's telling us how fast or how slow the joules of energy can move from each of these substances. So again, solid water, 2.1 joules per grams degrees Celsius. Liquid water jumps up to 4.18, and then we jump back down to 2.2 for gaseous water. When water melts or freeze, it'll move 334 joules per gram. And then if water boils, evaporates, or condenses, it'll move 2,260 joules per gram. So again, depending on what type of state or what the water is doing, the thermal transfer will vary, and we have to know that type of thing. This table will be of crucial importance to us in skills 3.5 and 3.6 because it gives us some constants that we're going to use with specific heat equations. Let's go ahead and let's write out those equations right now so we can see them. Please write this into your notebook. So what we want to do first is kind of make a dividing line to show that these two things are different, these two sides. These constants will funnel into this equation. Q equals M times H. And you'll either get a V or an F in that spot, in that subscript right there. These equations will funnel into an equation called Q equals MCAT. And again, in the next videos, we specifically go over these these equations, but we want to make sure that we understand that these numbers only correspond to this equation. These numbers here only correspond to this equation. These equations will be used to help us come up with a definitive number that we can use for thermal transfer. Anytime we get a fraction of some sort, like this or like this, we understand it to be a rate. So this is a rate, and then that's a rate. And what we can do for rates is graph them, and we can also write them as for every statements. So understand that slope equals a rate, right? And the rate that slope is rise over run. So believe it or not, these two items here, these two numbers, can actually be graphed. What we want to do is go ahead and write the for every statements for each, and that really kind of hones in on what the skill for today's lesson is. Let's go ahead and write out this first number as a for every statement. So here's what it says. And we'll draw an arrow so we know that we pulled it from here. Here's what it says. For every 1 gram of water, it will take 334 joules of energy to melt or freeze it. So for every 1 gram of water, it will take 334 joules of energy to melt or freeze it. Please notice that these action verbs are critical. So melt or freeze corresponds to melt or freeze here. Now let's go ahead and write out our second for every statement. Right, so another arrow, and we'll start writing here. So here's what this one says. For every 1 gram of water, it will take 2,260 joules of energy to boil / evaporate / condense it. All right, let's take our highlighter. And again, let's highlight the verbs that are really important. So these right here. And these verbs correspond to these actions here. So at this point, we've pretty much hit learning target 3.4. It's all about just writing out these rates into words. But if you'd like to kind of hang in there and see me graph these, go ahead and keep watching. Every time I hear the word for every, I think of rates, and I also think the fact that we can graph it, okay? So here on the bottom, I've come up with two plots. So one is for heat of fusion, and one is for the other for everything, heat of vaporization. And what I've done is these are joules versus grams graphs. Okay, so that's exactly what we find as our units here. So joules per gram, joules per gram. Notice that the axes of our graph will correspond to that. So to scale these the same, what we're going to do is we're going to go up by 2,000. So this will be 2,000. This will be 4,000. And then up here we'll have 6,000. And then we'll scale the bottom a little different. We'll do 1 gram. And then we'll do 2 grams there. Remember, we always start at the origin, 0, 0. Let's go ahead and scale the other one. 2,000, 4,000, 6,000. And then again, we'll have 1, and then we'll have 2 right there. So the heat of fusion says that for every 1 gram, we have 334 joules spent. So let's go ahead, let's put in that first one. So here's 1 gram. 1,000 is going to be somewhere here in the middle. So that means 334 is going to be way low down here. So now for 2 grams, all we have to do is we have to double 334. So 334 times 2 comes out to 668. Let's go ahead, let's find that. That's going to be somewhere still pretty darn low, okay? We're going to take our pen, start at the origin, and graph these out. All right, there's our first rate done. All right, so the magic number for heat of vaporization, remember, for 1 gram was 2,260. So let's go ahead and find that. So here's 1 gram. 2,000 is here. 2,260 has got to be right up above it a little bit. So now for 2 grams, remember, we have to multiply this number out by 2. 2,260 times 2 gives us 4,520. All right, so let's go ahead, let's find that. So here's 2 grams. Here's going to be 5,000. 4,500 will be somewhere in the middle. We'll kind of trace that out a little bit. And here's going to be our rough sketch. That's going to be our second number here. Let's grab this guy out. So not perfect line, but you can kind of tell where everything should be. So now since we have the rates visually described, which rate is higher, you would say? I would say the right side. And does that make sense when we look back at the original numbers? Absolutely. This rate of thermal transfer is much, much, much higher than this rate of thermal transfer, and we totally see that in the graphs. All right. Thank you for hanging in there. At this point, I'll conclude the video, and as always, have a great day. Thank you.